Hello everyone, welcome back. We're going to continue our review of complex numbers. And there's a lot of problems to talk about in this next topic, so I split it up between two different videos. This is part one. The topic we're going to discuss is complex number arithmetic. Now the goal overall for this discussion, we'd like to solve equations involving complex variables. I'll put an example of an equation like that up here. And as usual, just like we do in any other kind of algebra, our goal in working on this equation is to get z, that's the unknown. We want to get z by itself on one side of the problem. And whenever we're working with complex numbers, we always want to put our final answer in standard form, a plus bi. And to get it in that form, we need to use the operations of arithmetic. So addition, division, etc. And that's what we're going to look at in this lesson. The first thing that I want to talk about is addition and subtraction. A problem of that type is just a matter of combining like terms. Let's take a look at an example. I set that up here. I have complex numbers z and w, and I want to add them. Okay, so I plugged in the values for z and w, and then I combined like terms. And what that means in complex numbers, the real parts are like terms. So 2 plus 6 is 8. Also, the imaginary parts are like terms. So 3i minus 6i gives me negative 3i. Doing a problem involving subtraction is very similar. I laid out the steps here. The only thing you need to be careful of, as always, is working with a minus sign. Notice how I distributed that minus sign through the second group of parentheses on the right-hand side. In particular, I have positive 6i at the end of the second line. That comes from distributing that minus sign. All right, so that's an example of the algebra that we would use to do addition and subtraction. In addition to the algebra, I'd also like to take a look at the geometry of these last two examples that we did. It turns out that adding or subtracting complex numbers is actually a version of vector addition, something that you should be familiar with from physics. So I went ahead and set up the addition problem for the numbers that we've been working with, and you can see that result here. I went ahead and graphed them as points in the complex plane. Now the next thing we're going to do is represent those points as vectors. So I've done that here. Each vector starts at the origin and ends at the point in the complex plane that we just defined. Now remember that we have, for a vector, we have a tip and a tail. So here the tail of the vector is the part on the origin, and the tip is where you see the arrow. When we add two vectors together, the addition is tip to tail. For the problem that we're looking at, what I did is I took the second vector in our sum, and I moved it up so that its tail is located at the tip of the first vector. Then we know that the result of our addition is what's shown in the diagram. Turns out that's going to be 8 minus 3i, and you can see that the picture we have here matches up with the algebra that we did earlier. Next, we're going to look at the subtraction problem, and the ideas here are very similar. So I laid out my points in the complex plane. I want to represent those points as vectors. And then if we're going to subtract vectors, we think of adding a negative. So I got to find the negative of that second vector. What that means is we reflect that second vector across the origin, and you can see that I've done that here. Finish off the problem the exact same way that we did the last example. So we're going to add these vectors tip to tail, and my final answer is minus 4 plus 9i. You'll notice that this matches the arithmetic that we did earlier. This concludes our discussion of addition and subtraction. The next thing we're going to do is go on and talk about multiplication. Multiplying these numbers is going to be an application of the FOIL process. After we do that, we're going to simplify I squared and combine like terms. Let's take a look at an example problem. So I want to look at this product here. I set that up. You can see on the first line, I substituted in the values for z and w that I have in this example. And then I went ahead and did the steps of the FOIL process. Notice that in the last term on this line, I have an I squared. In our last lesson, we talked about the fact that I squared is defined to be minus 1, and so I'm going to carry out that substitution. Notice that my plus 3 I squared is now minus 3. For the last step, I'm going to combine my like terms, and that gives me the answer that you see here. All right, this is an example of how we would lay out the steps for multiplication. I want to take a look at the same problem in terms of the geometry of the complex plane. So I went ahead and graphed the points for these numbers. Again, we're going to want to think of these points as vectors. And then the answer that we got, so I represented that answer as a vector. What I want you to think about, what does this picture represent? This is something that you saw before, but it may have been a while. So the picture that we're looking at here, it's actually related to the idea of representing the plane using polar coordinates. We're going to come back to this in our next lesson, and we're going to talk about this idea in detail. It's actually very important to the physics problems that we're going to work on. I wanted to introduce it here. Just think about it and see what you remember. But put it aside for now. We're going to come back to this idea a little bit later. Okay, the next thing that we're going to do is take a look at two special cases, two special patterns involving the multiplication of complex numbers. The first of these patterns has to do with powers of a complex number. As long as our power is an integer, as long as our power is a whole number, we can think of raising z to a power as a type of multiplication. I set up a problem like that here. So if z is equal to 1 plus 3i, then z squared is the multiplication problem that you see. As far as carrying out the steps, it's exactly the same as what we've already done. I laid all of that out here, and the final answer that I get is minus 8 plus 6i. We can do the same thing for any whole number power of z. For example, z to the fifth would lead to the setup that you see on the right-hand side of the equation here. And then I could proceed by multiplying kind of one pair at a time. So I did a little bit of that here. Now I'm not actually going to finish this problem because it's kind of messy. But I think you can see the idea. Now what do you think? Would it be possible to find, say, z to the 100th power using this method? Yes, it would be possible, but it is definitely not something we would want to do by hand. It would be very difficult. Another question, what about like z to the 1/2 power? That is not going to work by this method. That is not an integer power. And so we're not going to be able to find it just by multiplying things out. Now it turns out both of those questions that I just asked can be very easily solved if we use the polar coordinate form of a complex number that I mentioned earlier. So powers in general, something that we're going to come back to. In particular, powers of the number I, that's something that we're going to talk about in detail right now. It turns out that there's a particularly simple pattern for powers of the number I. And it's something that we're going to use a lot in problems we have coming up. Let's take a look at this pattern. Okay, so the first power I want to talk about, I squared equals minus 1. This comes from the definition of I that we saw in our last lecture. Next, For I to the third power, I'm going to break that down, separate it out into I squared times I. And then I'm using the first result, the result from the first line. And finally, I know that minus 1 times I can just write that. Its simplest form is probably minus I. Next step, so I to the fourth, I'm going to break that down as I squared times I squared. Each of those numbers is minus 1. And when I carry out the last multiplication, the result is just 1. Again, what I just found is going to be very important. Whenever I multiply by 1, I don't change anything about my answer. So the fact that I to the fourth power is just 1 is going to make the rest of my calculations very easy. Let me show you what I mean. So the next power in sequence is I to the fifth. When I break that down into I to the fourth times I, well, the fact that I to the fourth is 1 makes my work very easy. I know my final answer is just I. I can use this same idea for the other powers that I want to calculate. Here's how I would set up I to the sixth. It simplifies down to I squared or minus 1. Okay, next I laid out the work for I to the seventh. It equals minus I. Here's I to the eighth. And notice that I'm back at the value 1. And then the fact that I to the eighth equals 1 will let us simplify powers higher than 8. The same pattern continues forever. And so what we can say is that any multiple of 4, well, if we have I raised to that power, then that answer will be 1. We can then apply this idea to simplify any integer power very easily. I set up an example here. Let's say we want to find I to the 50th power. What we think of in this problem, we want to divide by 4 and use that to simplify. I laid out the steps here. Notice that I'm doing the kind of division where we report a remainder, not decimal division. So another way to write the answer that I calculated, well, I can write that the way that you see here. So I went from division to multiplication. I set that up here. So you can see that I changed that exponent 50 into the form that I got from my division problem. Next, I'm going to apply a property of exponents as you see here. And then notice that the first piece of that product I have, well, that's just a multiple of 4 up in the power, and we know that that simplifies down to 1. So the power of I that I'm working with here becomes 1 times I squared, and that answer is just minus 1. So using this idea of dividing by 4, we can find any integer power of I very easily. As I said, this is something that's going to come up a lot in future problems, and so these powers are something that I'm going to ask you to practice on the homework. Okay, so powers of a complex number, whole number powers. That was sort of our first special topic involving multiplication. The last thing that I want to do in our current lesson is talk about another special case involving multiplication, and that is multiplying a complex number by its conjugate. Do you remember from our last lesson? We find the conjugate of a number by changing the sign on the imaginary part only. I set up a problem like that here. Now notice on the right-hand side, once I plug in the definition of the conjugate, it's just a standard multiplication problem. And so we finish off the exact same way that we've done our previous examples. I laid out all the steps here. Pause if you need to and check out what's going on in this example. Now, the reason that I want to talk about this in particular, it's kind of a special case. It's because even though we're starting by multiplying two numbers, they're not real numbers. They have a non-zero imaginary part. But notice that our final answer is 74. That's a purely real number. Now, this is not a coincidence. This happens every time we multiply a number by its complex conjugate, and that is why this is an important pattern. And that brings me to another kind of goal for our class. So one thing that we're going to work on is writing proofs. Now this is a minor goal, but it is something that I'd like you to improve. And so a problem on the homework that I have, I've kind of laid out the steps of this proof, and I'd like you to fill in the details. So in this video, we've talked about addition, subtraction, and multiplication. And that's all that I'm going to cover for right now. In the next lesson, we'll come back to this and finish it off by discussing division.